Good morning, everyone. I welcome you all to session on programmable logic controllers, session 9 of Unit 5. In the last session, we have discussed in detail about the timers, why a timer is used, a on delay timer, which is going to delay an event, and an off delay timer. Now, in the current session, we are going to discuss about retentive on delay timer, cascade timers, simple counters, and finally up counter and a down counter. Coming to retentive on delay timer, retentive on delay timer works like the on delay instructions with one main exception. Whenever the rung goes false on the RTO instruction, it will retain the ACC value. When the rung becomes true again, the ACC value will pick up from where it is left off. One good application of the RTO or the retentive on delay timer is an hour meter to indicate the total runtime for machinery. Since RTO does not reset itself, when the rung goes false, the RES instructions must be used to reset a timer. In this example, once the machine accumulates 1 hour of runtime, a light might come on indicating that lubrication needs to be engaged. Once the operator lubricates the machine, he can reset the hour meter. Another example is the coffee vending machine. So we have put a token to have a cup of coffee, but in between the power goes. ಸೊ ಆಗೇನಾಗುತ್ತೆ, ಬರೀ ಹಾಫ್ ಕಪ್ ಮಾತ್ರ ಕಾಫಿ ಫಿಲ್ ಆಗಿರುತ್ತೆ. ಮತ್ತೆ ಕರೆಂಟ್ ಬಂದಾಗ ಸೊ ನಮ್ಮ ಟೈಮರ್ ಎಲ್ಲಿ ನಿಂತಿತ್ತು ಅಲ್ಲಿಂದ ಮತ್ತೆ ಶುರುವಾಗುತ್ತೆ. ಸೊ ಕಾಫಿ ಕಪ್ ಅಲ್ಲಿ ಎಷ್ಟು ಕಾಫಿ ಬಂದು ಫಿಲ್ ಆಗಬೇಕಿತ್ತು ಅಷ್ಟು ಮಾತ್ರ ಫಿಲ್ ಆಗುತ್ತೆ. ಸಪೋಸ್ ಇದೇ ಕೇಸಲ್ಲಿ ನಾನೇನಾದರೂ ಕೂಡ ನಾರ್ಮಲ್ ಟೈಮರ್ನ ಯೂಸ್ ಮಾಡಿದ್ರೆ ಕಾಫಿ ಕಪ್ ಏನಾಗ್ತಾ ಇತ್ತು, ಓವರ್ಫ್ಲೋ ಆಗ್ತಾ ಇತ್ತು. ಕಾಫಿ ಕಪ್ಪಲ್ಲಿ ಕಾಫಿ ಓವರ್ಫ್ಲೋ ಆಗ್ತಾ ಇತ್ತು. So this is the ladder diagram for the retentive on delay timer. So we have the we have the switch for switching on the machine. So when we have retentive timer is on, when the done bit goes high, so what happens, there is a we get a we get a signal that the machine has accumulated 1 hour of runtime, so we need to lubricate it. So once I acknowledge this signal, then again the machine resets. That is, the machine will be running and the machine will be stopping in between. So the retentive timer is going to calculate the total runtime of the machine for 1 hour. So after the 1 hour, say a lamp glows to lubricate it, a red lamp glows, it is the time to lubricate it. So once I acknowledge that lamp signal, so again the my retentive timer again gets reset. So I will be switching on and switching off the machines many times, even though I am switching on and switching off the machine run times. So the timer is not going to reset as in the case of on delay timer or the off delay timer. Let us see a video on delay. Sorry, let us see a video on retentive on delay timer.
For applications requiring the accumulated time to be retained if there were a system fault or the rung condition goes false, a retentive timer on is used. The retentive timer on is enabled and begins timing when the input conditions are true. By changing the rung condition to false in the retentive timer circuit, the accumulated value stops timing and retains the time recorded until the rung condition goes true again. As the accumulated value reaches the preset value, the done bit goes true and enables the output. A programmed reset instruction with same address of the timer is used to reset the retentive.
So we use the reset button to reset the timer after the total retentive time is over. Coming to the cascaded timers. Cascaded timers are used when individual timers do not have enough time-based intervals for a particular application. When the application especially requires a longer time delays, then a single timer, it is not possible for us to obtain the time delay using a single timer. In such cases, we use multiple timers. When the first timer times out, it becomes an input to start the second timer. Two timers are used to extend the time delay here. The first timer output T4.40 done bit acts as input to the second time. So in cascade timers, we are using multiple timers to extend the time delay. Coming to the next topic, that is a simple counter. What is a counter? The counter counts the number of events that occur on an input. Instead of counting the time, it just counts the number of events. There are two types of counters, up counter and a down counter. Up counter, in an up counter, whenever a triggering event occurs, an up counter increments the counter. In a down counter, whenever a triggering event occurs, a down counter decrements the counter. The practical example of a up counter, that is CTU, and a down counter CTD is explained with the help of the pizzas going into the oven and the pizzas coming out of the oven. So we use up counter at the entry where the pizzas are entering the oven, and we are using a down counter where the pizzas are coming out of the oven. Each time when pizza goes into the oven, the ACC value is incremented by 1. Each time when the pizza comes out of the oven, the ACC value is decremented by 1. Difference in ACC value of the CTD counter and the CTU counter determines how many pizzas are there in the oven at a given time. So the done bit is used to shut the conveyor down if pizzas are going into the oven and not coming out. So this is the ladder diagram for the the pizzas which are entering the oven and exiting and coming out of the oven. A proximity switch 1 is used to detect the pizzas which are entering the oven. So we are using a count up counter here. So and there is another proximity sensor to sense the pizzas which are coming out of the oven. So which is going to count down. We are using a countdown timer, and we are going to reset it we reset the uh, counters using the reset button. So this is the ladder logic for the CTU and CTD implementation. So let us see a video on up counter and the down counter.
Alright, so in this video we'll study and learn the counters. Now the counters are used. This is the counter. See, this is address is C5 colon O colon 1 2 3 4. Now the counters are used to count the number of intervals, count the number of events which are at the input. Suppose it can be used in a conveyor system where we need to count the number of bottle passing or the number of boxes or any number of events. If we need to count, we can use the counter. So to use a counter, let's go to this counter and timer and counter block, and let's take CTU, which is count up. Okay, I'm taking this counter after this I0 colon 0. So this will count the number of times this input is on. Alright, so the same thing as timers. I'll take here C5 colon 0. This is the counter 0. Then at preset, this is the number of counts which I want that counter should count. So let's take it as, let's 6. So similarly, it has count up bit and done bit. So done bit will be on when the count 6 has been completed. So similar as the timer, in which the time completed and done bit is on. Similarly, we have done bit for the counters. So let's take a bit here and I'll write it as C5 colon 0 slash DN. Now this is the done bit of my counter C5, and let's take an output O colon 0 slash 0. That is the output which I want to be on when the count is completed as 6. So this is to notify that number of count is completed by taking an output O colon 0 slash 0. So now the logic says that if I press this I0 for 6 number of times, or 6 times, this done bit will be on and output will be on. So let's check it out. So I'm pressing this once. So you can see that I have kept on pressing it. So it will only count 1. So I'm pressing it again, 2, again, 3, 4, 5, and at 6 my output is on. Now I have released the input. Still the output is on because it will retain the output. It will not depend that input is on or not. It will just count the number of pulses. That's why the output is latched. So to unlatch this output, what we need to unlatch the to unlatch, or you can say that to reset this counter. So again, similar as to timers, we will take another bit to reset the counter. So I'm taking a rung here and another I colon 0 slash 3. This is the input bit, and I'm going to reset this counter by reset command here, and I'll give an address C5 colon 0, enter. So let's download that into the PLC. So this bit has been introduced to reset the counter or to reset the output parallelly. So let's count again, 1 2 3 4 5 6. Output is latched. Now I'm going to turn on this I3, which will reset the counter and it will reset the output. Oh, you can see here, because the accumulator is not equal to preset, that's why done bit is off and output is on. So let's try again, 1 2 3 4 5 6. Output is latched, and again output is reset. So that was about counter up, count up. Now similarly we have count down, which will decrement the counts. Oops, sorry. So let's go for count down now. So instead of CTU, I'll take CTD, same address. Now here something needs to be understood, that I'm going to put value in accumulator. I'll tell you why. Because it will count down the accumulator. Alright, earlier the accumulator was incrementing, now accumulator will decrement. So that's how you can use a counter to decrement the values. Now what will happen in this case? Let's see. Initially the accumulator is at 10. Alright, so when I press the accumulator, it will keep on decreasing. Right now accumulator is greater than preset. So the condition says when accumulator is equal to or greater than preset, output is on. So when I press this button IN0, you can see accumulator will start decreasing by pressing this IN0. Accumulator is decreasing. So when accumulator become less than 0, alright, now it is equal, As soon as it goes less than 0, output will be off because this is done. Okay, so even if I press it again, it will remain off. Now, but if I reset that, it will again will be on, and it will be off only if I press it 10 times. Oh, sorry. Accumulator will be reset if I press this button. It will go to 0 because I have done the reset. It will not go to 10. So that's all about countdown. It will start the counting in the downward directions. Or in the other way, what you can do is, if you want accumulator to be at 0, if I initially putting this at 0, I can take preset value in minus. This is another way of working with this counter, because this is a countdown. If I press this IN0 now, it will go to the minus. It will go to -1, -2, -3. So in other way, you can use countdown and count up in other of the application. So right now it is on because 0 is greater than -10. It is going to minus. So as soon as it goes -11, output will be off because accumulator is greater than this preset, less than this preset. So when I reset this accumulator again, output will be on. Accumulator is more. Now when I press it again up to 11, accumulator is less than preset, so output is off. So that's countdown. It will always decrement the accumulator, and count up will always increment the accumulator. So that was all about counters, count up and count down, and you can use in many different applications of counting the events. That's all about counters.
On the completion of this session, you should be able to know what a retentive on delay timer is, what are cascade timers, simple counters, especially up counter and the down counter. So these are the few references. Now coming on to the MCQs. The first MCQ is, the operation of PLC retentive timer is similar to that of an electromagnetic pneumatic timer, electromechanical motor driven timer, off delay timer, on delay timer. The answer is B. It is similar to electromechanical motor driven timer. The second MCQ is, unlike the on delay timer, the RTO, the retentive on delay timer, requires an or a timer reset instruction, input condition instruction, internal relay instruction, instantaneous contact instruction. The answer is A. Timer reset instruction. When the timing of a device is not reset on a loss of power, the timing is said to be A. Continuous, holding, retentive, safe. The answer is C. Retentive. Programmed counters can count up, count down, be combined to count up and down all of these. The answer is D. All of these. The counter instruction is found on A. All PLCs, B. Small size PLCs, C. Medium size PLCs, D. Large size PLCs. The answer is B. Small size PLCs. The PLC counter instruction is similar to the internal relay instruction, transitional contact instruction, relay coil and contact instruction, timer instruction. The answer is D. Timer instruction. The output of a PLC counter is energized when the accumulated count equals to the preset count. Preset count is greater than the accumulated count. Counter input rung is true. Counter input rung is false. The answer is A. The accumulated count equals to the preset count. Which of the following is not usually associated with a PLC counter instruction? A. Address. B. Preset value. C. Time base. D. Accumulated value. The answer is C. Time base. A PLC up counter CTU counter counts scan instructions, true to false transitions, false to true transitions, both B and C. The answer is C, false to true transitions. When the up counter reset is set to true, the following happens. The preset value is set to 0. The preset value increments. The accumulated value is set to 0. The accumulated value is set to maximum. The answer is C. The accumulated value is set to 0. The accumulated count of a CTD counter increments with each true to false transition, decrements with each true to false transition, decrements with each false to true transition, increments with each false to true transition. The answer is C. It decrements with each false to true transition. The accumulated count of a CTU counter increments with each true to false transition, decrements with each true to false transition, decrements with each false to true transition, increments with each false to true transition. The answer is A, increments with each true to false transition. Thank you.